now I'm going to start transcribing, but whenever I come to a word that is a quantum word, I'm going to write in green the classical word. And I'm just going to assert that if we follow the resulting program, the code is going to work. I'm going to use a word that I'll define a little later. I'm just going to say canonically immersed. And by canonically immersed, immersed was there before. By canonically, I'm going to mean very specifically that it preserves metric and symplectic structure.
Yes. Both of them, to me, mean some kind of description of the geometry.
Yes. There are several equivalent ways, and the way that I use when I want to understand the difference between them is this. I'll try several different ways. Both of them can be viewed as objects that accept two vectors and return a number. The metric form returns the dot product of those two vectors. The symplectic form, the metric form returns the cosine of the angle between those two vectors. Mm-hmm. The symplectic form returns the sine of the angle between those two vectors. So that's one way to say, and it's a rigorous way, to say what a symplectic form and a metric form actually do. Now another way to say is that...
well, what's the interpretation of, I mean, the metric has the dot, metric has this interpretation of dot product.
Yeah, so here's what they like.
And the cosine just basically means the projection of one onto the other, but what's the other one mean?
Okay. A symplectic form of two vectors is geometrically associated with the parallelogram defined by those two vectors.
Uh-huh.
If those two vectors are the same vector, that parallelogram is 0.
Uh-huh.
If those two vectors are different vectors, then that parallelogram is non-zero.
Mm-hmm.
But there's another way to think of it that is equivalent but not obviously equivalent, and that is that a symplectic form, that these are both tools for converting vectors to one forms. And that the way now this is the way I think of it really. If I think of a vector as a little arrow, then the metric form converts that arrow to a one form, and that one form is like a set of parallel surfaces. The longer that vector is, the closer these surfaces are together. A symplectic form also converts an arrow to a set of surfaces, but in the symplectic form, those surfaces are at right angles. And so you can, and then you can go back and forth. A metric form lets you go back and forth between surfaces and vectors. A symplectic form lets you go back and forth between surfaces and vectors. And if you keep applying, well, you could say, all right, I'll start with a vector, I'll apply a symplectic form. Now I'll take the inverse of the metric form and convert that back to a vector. And I'll get a vector that points in the opposite direction. And that process of taking operations and converting vectors into the opposite directions, that also appears back in Kähler manifolds, and it's associated with numbers I. So we'll see examples of this when we start working the circle problem. If we ask ourselves at every stage, all right, I have a vector, I have a one form, what is the meaning of that vector, what is the meaning of that one form? We will see examples of this in the circle problem. So there's really no answering this unless you really have this idea of vectors and forms under control and have worked a lot with toy problems with vectors and forms. And we're going to work with that toy problem. If you just work with the toy problem, you never get the abstraction. If you just work with the abstraction, you never get the toy problem. You have to work with abstractions and toy problems. The order is irrelevant, but you have to go back and forth between them over and over again until the pictures, the toy problems, and the abstraction all merge together. So it's a little bit like, you know, blending the gravy and the potatoes. It doesn't matter which you add first because you're going to do a lot of blending later on. So it doesn't matter, you know, which you do first. You're going to do a lot of blending of abstraction and pictures and toy problems as you go. You could write a computer program that could do that. But that's not the way humans really use these dots on paper. A human really has to play the music until looking at the dots on the paper, you hear the music, and hearing the music, you can visualize the dots on paper. Only then do these two skill sets merge. And there's no way that you could learn first one and then the other. You have to hear the music and learn the musical notation. You have to do that as a parallel, organic growing process. There's just, you know, it's not something that can be achieved by any amount of logic or by any amount of just intuitive listening. That's why Arnold has this wonderful quote where he says, the left side of the brain understands languages and symbols, and the right side of the brain understands geometry, and when both sides of the brain are working, then you're really understanding how Hamiltonian mechanics works. So right now we're kind of working on the left side of the brain. We're going to work on the right side of the brain in a while and see if we can get those two sides of the brain. So when we produce our maps, this is going to be the key phrase that our code has to respect. If we specify a map, we can pull back a metric structure. There's no ambiguity about that. We can pull back a symplectic structure. There's no ambiguity about that. And then the question is that symplectic structure natural? And that's something we can test. And natural is going to have two meanings. It's going to mean that the symplectic structure itself is natural, and it's also going to mean that when we push forward tangent vectors, they have a natural embedding. So this word natural is the key. And we'll be defining what that means. The map from these coordinates to Cartesian coordinates on H. Then we introduce a bundle structure. We introduce bundle structure. What kind of bundle structure? Natural bundle. Well, now, you know what I'm going to do? Rather than keep going, I'm actually going to switch to phase 3 and write some code. And after I've got the code all working, then I'll write the last 4 lines of this in a way that reflects the structure of the code. So what I'm going to switch over here is I'm going to switch to pictures. You know, this is kind of how he talked about music. It was clear that he thought about the music with both sides of his brain, and I only thought about the music with one side of my brain. My band teacher would have said I thought about music with no sides of my brain. In fact, he had a general opinion that pretty much nobody in 6th grade band had any brains at all, as a matter of fact. Marching band, I think, it's kind of a far side version of hell for a music teacher here. And I want to teach 6th grade marching band when I'm a professional musician. The marching was hard enough, but the music was really hard. So we're going to kind of sight read this music and move our fingers until suddenly we begin to say, you know, something's happening. There's some music here. It's not just black dots on paper and me moving my fingers. So that's what we're going to hope happens with our Mathematica code. We're going to type code in and draw pictures until we start to hear the music. So let's do at the top, I'm just going to transcribe this. Particle in bowl. The particle is a stand-in for a point. The bowl is a stand-in for a potential. The trajectory is the path of the point in the potential. Joe Garbini could probably draw a bowl a little more nicely than I could. There's a bowl. This must be the outside of the bowl. This must be the inside of the bowl. This must be the bottom of the bowl. This must be a particle in the bowl, starting out in a given direction with a given velocity. This must be the trajectory of the particle in the bowl. And this must be the projection of the trajectory onto the xy plane. If we plot that as an xy plot, this is called a parametric plot, we should get a circle. And if we plot it as a plot of coordinates versus time, but we do several of them, then x of t, we'll say we'll start at 0 and go up and down in a sine wave. Y of t, if x of t is 1, we're going to start y of t in a different color. That'll go to 0. It'll go to minus 1. It'll go to 0. It'll go to plus 1. It'll go to 0. This is y of t. And I haven't yet said about the velocity, but the momentum associated with x will be, well, unfortunately, if I start drawing, I could draw the momenta on this curve too. I could probably get one where I had 4 curves in 4 colors with 4 quadratures, but I'd have to start things out appropriately. So I'll think about that for a while. But this will be good enough. Eventually I'll draw x of t, y of t, the momentum associated with x and the momentum associated with y. Yes, that would have worked perfectly. All right. But that will be reserved for another lecture, and we're going to declare victory for now. Take this two-dimensional system and pull it back onto a wire, and if I arrange the wire to be the geometry that the path would have followed anyway, then I want the pullback results to be indistinguishable from these results. More generally, if I pull back not onto a wire but some arbitrary shape, then I want geodesics in this larger space when integrated on the smaller space to be geodesics of that smaller space. And if I do those two things, I'm going to regard the pullback as canonical from this Hamiltonian point of view. And in particular, if I take atoms unconstrained, roving around in a box, and I constrain their bond lengths to be fixed values, and I apply this formalism without alteration, I should get the colliding water molecules of Frenkel and Smith. So all of that, if we align our thinking properly and align our code properly, should be just a matter of asking Mathematica to keep track of more indices. Just as in our quantum system, if we could do 2 interacting spins, then ramping up to 20 interacting spins was just a matter of waiting longer for the code to run. Okay,